Hey Casey, did you know that before 2017, most AI researchers thought you needed really complex neural networks with all these fancy recurrent connections to process language?
Yeah, and then this paper came along and basically said, nah, you just need to pay attention. Talk about a paradigm shift.
Welcome to another episode of Totally Unprofessional Peer Review, the podcast where we break down groundbreaking research papers without the academic jargon.
That's right. I'm Casey Park, a developer with an eye for structure and flow in these papers.
And I'm Max Stone, coming at these papers from a theoretical perspective with a focus on metrics and methodology.
Today, we're diving into what might be the most influential AI paper of the last decade. Attention is all you need by Vaswani and colleagues.
This paper introduced the transformer architecture, which completely revolutionized how we approach natural language processing. Before this, everyone was using these complex recurrent neural networks that process text one word at a time.
But these researchers had a radical idea. What if we just let the model look at the whole sentence at once and figure out which words should pay attention to each other?
And not only did their approach work, it absolutely demolished the previous state of the art results while training in a fraction of the time.
It's basically the paper that made GPT, BERT, and all those AI chatbots possible. So if you've ever wondered why your AI assistant can actually understand what you're saying instead of just spitting back memorized phrases,
Or why we suddenly went from barely functional machine translation to systems that can translate almost as well as humans in just a few years.
then stick around because, as it turns out, attention really is all you need. Well, that and a few billion parameters.
So, Casey, we're diving into what might be one of the most influential papers in modern AI. Attention is all you need. This paper introduced the transformer architecture, which has completely changed how we approach natural language processing.
Absolutely, Max. And what makes this paper so revolutionary is right there in the title, the idea that attention is all you need. Before this paper, the dominant approach to sequence tasks like machine translation relied on complex recurrent or convolutional neural networks.
Right, and those traditional models had some fundamental limitations. Recurrent neural networks like LSTMs or GRUs processed data sequentially, word by word, which created a bottleneck for parallelization.
Exactly. The paper points out that this inherently sequential nature precludes parallelization within training examples. In other words, you can't process the whole sentence at once. You have to wait for each word to be processed before moving to the next one.
And that becomes a huge problem with longer sequences. The paper's authors proposed something radically different, a model that completely eliminates recurrence and convolutions, relying entirely on attention mechanisms instead.
It's worth noting that attention mechanisms weren't new, they'd been used before in conjunction with recurrent networks. But the transformer was the first model to say, hey, we don't need recurrence or convolution at all. Attention alone can handle this.
And that was a bold claim. Let's break down how the transformer architecture actually works. The paper includes a really helpful diagram that shows the overall structure.
Looking at this diagram, we can see the transformer has an encoder-decoder structure, which was common in sequence-to-sequence models, but the implementation is completely different. Both the encoder and decoder are composed of stacks of identical layers, 6 in each stack, according to the paper.
And if we look at the encoder on the left side, each layer has two main components, a multi-head self-attention mechanism and a position-wise feed-forward network.
The decoder on the right is similar but has an additional multi-head attention layer that focuses on the encoder's output. There's also that masked multi-head attention at the bottom, which prevents positions from attending to subsequent positions, essentially making sure the model doesn't peek at future words during training.
Let's focus on the attention mechanism, which is the real innovation here. The paper describes it as mapping a query and a set of key-value pairs to an output. They call their specific implementation scaled dot product attention.
Right, and this diagram shows how it works. Essentially, you compute the dot products of the query with all keys, divide by the square root of the dimension of the keys, and apply a softmax function to get weights. These weights are then applied to the values.
The formula they give is attention QKV, a softmax QK transpose divided by square root of DK times V. It's a way of determining which parts of the input sequence the model should focus on when producing each part of the output.
But they didn't stop there. They introduced what they call multi-head attention, which lets the model jointly attend to information from different representation subspaces at different positions.
Exactly. Instead of performing attention once with full dimensional keys, values, and queries, they project these into smaller dimensions multiple times, creating multiple heads, and perform attention in parallel. Then they concatenate the results.
It's like having multiple attention mechanisms that can each focus on different aspects of the input. Their experiment showed that having 8 attention heads worked best, with either too few or too many heads hurting performance.
One question that immediately comes to mind is, how does the transformer handle the order of words? In recurrent networks, order is implicit in the sequential processing, but if you're processing everything in parallel, how do you know which word comes first?
That's where positional encodings come in. Since the model has no recurrence or convolution, they needed to inject information about the position of tokens in the sequence. They added these positional encodings to the input embeddings at the bottom of both the encoder and decoder stacks.
And they used sine and cosine functions of different frequencies for these encodings. The paper mentions they also tried learned positional embeddings and got nearly identical results, but went with the sinusoidal version because it might allow the model to extrapolate to sequence lengths longer than those seen during training.
What's really fascinating is how the transformer changes the computational complexity compared to recurrent or convolutional approaches. In RNNs, the maximum path length between any two positions is ON, meaning it scales linearly with sequence length.
Whereas in the transformer, because every position can directly attend to every other position in the self-attention mechanism, that path length is reduced to a constant. This is a huge advantage for modeling long-range dependencies in text.
Exactly. With RNNs, information from the beginning of a long sentence might get diluted by the time you reach the end. But with self attention, every word has direct access to every other word, regardless of how far apart they are.
The paper even includes some fascinating visualizations showing how different attention heads learn to perform different tasks. Some focus on syntactic relationships, others on semantic relationships. Some heads even seem to perform anaphora resolution, figuring out what pronouns like it or they refer to.
That's one of the nice side benefits they mention. Self attention can yield more interpretable models. You can actually visualize which words the model is focusing on when making predictions, which gives us insight into how it's making decisions.
I think we should also mention some of the other architectural details that make the transformer work so well. For instance, they use residual connections around each sublayer, followed by layer normalization.
Right, and they apply dropout to the output of each sublayer before it's added to the sublayer input and normalized. They also apply dropout to the sums of the embeddings and positional encodings. These techniques help prevent overfitting.
So, to summarize the revolutionary aspects of this architecture, it eliminates recurrence and convolution entirely, relying solely on attention mechanisms. It allows for much more parallelization during training, and it creates shorter paths between long-range dependencies in the text.
And all of this leads to models that can be trained much faster and achieve better results. The paper shows that the transformer outperformed previous state of the art models on translation tasks while requiring significantly less training time.
It's really no wonder that this architecture has become the foundation for so many of the language models we use today. The idea that attention is all you need turned out to be remarkably prescient.
Absolutely. And I think it's worth noting that while this paper focused on machine translation, they did mention that the transformer generalized well to other tasks. They probably couldn't have predicted just how versatile this architecture would prove to be.
That's the mark of truly groundbreaking research, when it opens up possibilities that even the authors didn't fully anticipate. Now, shall we move on to discuss the performance breakthroughs in more detail?
So, Max, now that we've covered the architecture of the transformer model, let's talk about what everyone really cares about, the results. And spoiler alert, they're pretty impressive.
Absolutely, Casey. The authors didn't just build a fancy new architecture, they absolutely crushed the previous state of the art results in machine translation.
Right? And what's even more impressive is how quickly they achieved these results. Let's break down the specific benchmarks they used.
They focused on two standard machine translation tasks from the WMT 2014 dataset, English to German and English to French translation.
For context, these are standard benchmarks in the machine translation world. The English German dataset had about 4.5 million sentence pairs, while the English French dataset was much larger with 36 million sentences.
And they used something called byte pair encoding for the English-German task with a shared vocabulary of about 37,000 tokens. For English-French, they used word piece vocabulary with 32,000 tokens.
Those are just fancy ways of saying they broke words into subword units, which helps handle rare words and morphologically rich languages better. But let's get to the juicy part, the results.
On the English to German translation task, their big transformer model achieved a BLEU score of 28.4.
For our listeners who aren't familiar, BLEU is a standard metric for evaluating machine translation quality. Higher is better, and 28.4 is.
It's more than 2 BLEU points better than the previous state-of-the-art models, including ensemble models which combine multiple systems. That's a massive improvement in the world of machine translation.
And for the English to French task, they had a BLEU score of 41.0, again outperforming all previously published single models.
But here's where it gets really interesting, Casey. It's not just about better results, it's about how efficiently they got those results.
Exactly. The paper mentions that they trained their base models for about 100,000 steps, which took only 12 hours on 8 NVIDIA P100 GPUs.
And their bigger models, which achieved those state-of-the-art results we just mentioned, took 300,000 steps, or about 3.5 days of training on the same hardware.
That's remarkable when you consider that the previous state of the art models often took weeks to train. The paper specifically mentions that their English to French model required less than one fourth the training cost of the previous best model.
And this efficiency isn't just a nice bonus, it's directly related to the architecture we discussed earlier. Remember how the transformer doesn't use recurrence or convolutions?
Right. Traditional sequence models process tokens one after another, which limits parallelization, but the transformer's attention mechanism can process all tokens simultaneously.
Exactly. The paper specifically states that a self-attention layer connects all positions with a constant number of sequentially executed operations, whereas a recurrent layer requires ON sequential operations.
Translation: in a recurrent network, if your sequence is twice as long, it takes twice as long to process, but with self-attention, the length doesn't affect the number of sequential operations needed. That's a huge win for parallelization.
And they also mention that the dot product attention they use is much faster and more space efficient in practice because it can be implemented using highly optimized matrix multiplication code.
Which is basically saying they're leveraging operations that modern GPUs are extremely good at. It's like they designed this architecture with hardware acceleration in mind from the start.
They also used 8 parallel attention heads, each with reduced dimensionality, so the total computational cost remains similar to single head attention while getting the benefits of multi-head attention we discussed earlier.
Smart engineering choices all around. You know, it's worth emphasizing just how big a deal this was in 2017. The paper literally says the transformer allows for significantly more parallelization and can reach a new state of the art in translation quality after being trained for as little as 12 hours on 8P100 GPUs.
And to put that in perspective, previous approaches like the ones from Kalkbrenner et al. Or Joe et al. That they reference would have taken days or weeks to achieve worse results.
I think Table 2 in the paper really drives this home. They estimate the computational costs by multiplying training time, number of GPUs, and the floating point capacity of each GPU, and by that measure, the transformer is dramatically more efficient.
Even their base model, not the big one, surpassed all previously published models and ensembles at a fraction of the training cost. That's a paradigm shift in the field.
It really is. And you know what's fascinating? This paper came out in 2017, and here we are years later still talking about it because it fundamentally changed how we approach sequence modeling tasks.
Absolutely. The combination of state-of-the-art results with dramatically reduced training time made this architecture incredibly attractive for researchers and industry practitioners alike.
And it's worth noting that while we're focusing on machine translation here, the authors did mention that the transformer generalizes well to other tasks. They specifically mentioned applying it successfully to English constituency parsing.
Right, which suggests that this architecture isn't just a one-trick pony for translation, it's a general-purpose sequence modeling approach that can potentially revolutionize many NLP tasks.
Which, spoiler alert, it absolutely did. But that's getting ahead of ourselves. The key takeaway here is that the transformer achieved better results faster than previous approaches, and that's a winning combination in any field.
To sum up this section, the transformer achieved a BLEU score of 28.4 on English to German translation and 41.0 on English to French, both state-of-the-art at the time, and it did this with training times measured in days rather than weeks, thanks to its highly parallelizable architecture.
And that efficiency comes directly from the architectural choices we discussed earlier, replacing recurrence and convolutions with attention mechanisms that can be computed in parallel across the entire sequence.
Exactly. Now, shall we move on to discuss how this architecture has been applied beyond machine translation?
Let's do it. I'm particularly excited to talk about how the Transformers design principles have influenced other areas of NLP and beyond. So, Max, we've covered how the Transformer architecture works and its impressive performance on machine translation tasks. But what really makes the model stand out in the AI world is its ability to generalize beyond what it was originally designed for.
Absolutely. And this is where the paper gets particularly interesting. The authors specifically tested the transformer's ability to generalize by applying it to English constituency parsing.
For our listeners who might not be familiar, constituency parsing is essentially breaking down sentences into their grammatical components, like identifying noun phrases, verb phrases, and so on.
Right. And it's a particularly challenging task for a few reasons. The paper specifically mentions that the output is subject to strong structural constraints and is significantly longer than the input.
And they also point out that RNN, sequence to sequence models, haven't been able to achieve state of the art results in small data scenarios for this task.
Which makes their results all the more impressive. For their experiment, they trained a 4-layer transformer with a model dimension of 1024 on the Wall Street Journal portion of the Penn tree bank.
That's about 40,000 training sentences, right? Not exactly big data by today's standards.
Correct. And they also tried a semi-supervised approach using larger corpora with approximately 17 million sentences from the high-confidence and Berkeley parser datasets.
And the results were, wow. According to Table 4 in the paper, the semi-supervised transformer achieved an F1 score of 92.7.
What's remarkable is that they achieved these results without any task-specific tuning. The transformer outperformed all previously reported models except for the recurrent neural network grammar.
And unlike RNN sequence to sequence models, the transformer even beat the Berkeley parser when training only on that smaller WSJ dataset of 40K sentences.
This really highlights one of the key advantages of the attention mechanism that we discussed earlier, its ability to handle long-range dependencies.
Right. The paper specifically mentions that learning long range dependencies is a key challenge in sequence transduction tasks, and the transformer addresses this by creating shorter paths between positions in the input and output sequences.
Exactly. The self-attention mechanism allows the model to directly connect any position in the sequence to any other position, making it easier to learn these long-range dependencies.
And it's worth noting that self attention wasn't entirely new when this paper came out. The authors mention it had already been used successfully in several tasks like reading comprehension, abstractive summarization, and textual entailment.
True, but what makes the transformer revolutionary is that it relies entirely on attention mechanisms, completely dispensing with recurrence and convolutions.
So let's talk about the broader implications here. What does the transformer's success on constituency parsing tell us about its potential for other NLP tasks?
Well, it suggests that the architecture is highly adaptable. If it can handle something as structurally constrained as parsing without specific architectural modifications, it likely has applications across a wide range of language tasks.
And the authors seem to agree. In their conclusion, they mention being excited about the future of attention based models and their plans to apply them to other tasks,
They specifically mention extending the transformer to handle input and output modalities beyond text, things like images, audio, and video.
which is pretty visionary considering how dominant transformer based models have become in those exact areas since this paper was published.
They also mention investigating local restricted attention mechanisms to efficiently handle large inputs and outputs. This is essentially foreshadowing the development of sparse attention mechanisms that we've seen in more recent models.
And there's one more research goal they mention that I find particularly interesting: making generation less sequential.
Yes, that's a fascinating direction. Traditional sequence generation has been very left to right, one token at a time. But the transformer's parallel nature opens up possibilities for more flexible generation approaches.
What I find most impressive about this paper is how the authors weren't just solving a specific problem, they were rethinking fundamental assumptions about how sequence models should work.
Absolutely. By showing that recurrence isn't necessary for state-of-the-art sequence modeling, they open the floodgates for a whole new paradigm in machine learning.
And the generalization capabilities they demonstrated with the constituency parsing experiment were just the beginning. Since this paper, we've seen transformer based models dominate virtually every language task imaginable.
Not to mention the cross-model applications they hinted at. It's remarkable how much of the current AI landscape was foreshadowed in this single paper.
I think that's what makes a truly groundbreaking paper, not just solving the problem at hand, but opening up entirely new research directions that others can build on.
And with that, I think we've covered the major points about the Transformers' versatility and applications. Any final thoughts before we wrap up this section, Casey?
Just that, it's fascinating to see how the author's intuition about attention being sufficient on its own has proven so prescient. Sometimes in research, less really is more.
Well said. Attention may be all you need, but a bit of research vision doesn't hurt either. Well, Casey, we've covered a lot of ground today with the transformer architecture. It's amazing how a paper that essentially said, let's try removing all these complex components, ended up revolutionizing the entire field.
Absolutely, Max. And what's fascinating is how this relatively simple idea of self attention has scaled to become the foundation of virtually every major language model today. It's a perfect example of how sometimes the most elegant solution is the one with fewer moving parts.
That's what makes great research so powerful. The transformer didn't just solve a problem, it changed how we think about problems. Thanks for joining us on another episode of Totally Unprofessional Peer Review.
And remember, folks, in the world of AI research, Sometimes all you need is attention, though in my dating life, I've found that approach gets mixed results.